Today we're going to be reading chapter 29, section 1. You can find this on page 775. Overview of our solar system. Earth is one of the 9 planets revolving around or orbiting the sun. All the planets, as well as most of their moons, are called satellites. Also called satellites, orbit the sun in the same direction, and all their orbits except Pluto's lie near the same plane. The planets of our solar system have various sizes, surface conditions, and internal structures. Scientists have gathered much information about our solar system through the use of technologies developed in the 20th century. But human beings have been watching the sky for thousands of years, and early ideas about the solar system were developed solely on the basis of Earth-based observations of the sky. Early ideas. When viewed from Earth, the planets slowly change position each night relative to the position of the stars. Therefore, ancient astronomers could recognize the difference between stars and planets. These astronomers assumed that the sun, planets, and stars orbited a stationary Earth in what is now known as a geocentric model, meaning Earth-centered. However, some aspects of planetary motion were difficult to explain with geocentric model. For example, the normal direction of motion for all planets as observed from Earth is toward the east. Occasionally, however, a planet will move in the opposite direction across the sky in what is called retrograde motion. The retrograde motion of Mars is shown in figure 29, 1a. The search for a simple scientific explanation for retrograde motion motivated early astronomers to keep searching for a better model of solar system. In 1954, Polish scientist Nicholas Copernicus suggested that the sun was the center of the solar system. In the sun-centered or heliocentric model, Earth and the other planets orbit the sun. This model provided a simple explanation for retrograde motion. In a sun-centered model, the inner planets move faster in their orbits than the outer planets do. As Earth bypasses a slower moving outer planet, as illustrated in figure 29 1b, it appears that the outer planet temporarily moves forward in the sky. Kepler's first law. The ideas of Copernicus were not initially accepted by the scientific community, but within a century, other astronomers were finding evidence that supported the heliocentric model. For example, from 1576 to 1601, a Danish astronomer, Tycho Brahe, made many accurate observations of planetary positions. Using Brahe's data, Johann Kepler's demonstrated that each planet orbits the sun in a shape called an ellipse, rather than in a circle. This is known as Kepler's first law. An ellipse is an oval shape that is centered on 2 points instead of a single point, as in a circle. The 2 points are called the foci, sing focus. The major axis is in the line that runs through both foci. It is the maximum diameter of the ellipse, is called, as illustrated in figure 29.2. You will experiment with the foci and the shapes of ellipses in the mini lab on this page. Each planet's elliptical orbit is a different shape and size, and the sun is always at one focus. For each sun-planet pair, half of the length of the major axis is called the semi-major axis. It is the average distance between the sun and the planet. For the sun and the Earth, it is 1.496 by 10^8 kilometers, or 1 astronomical unit. The average distance between the sun and each planet are measured in astronomical units, and therefore these distances are relative to Earth's average distance from the sun. Eccentricity. A planet is in an elliptical orbit is not a constant distance from the sun. When a planet is closest to the sun in its orbit, it is perihelion, and when it is furthest away, it is aphelion, as shown in figure 29.3. The shape of a planet's elliptical orbit is defined by eccentricity, which is the ratio of the distance between the foci to the length of the major axis. Eccentricity values range from 0 to 1. An eccentricity of 0 is the perfect circle, and an eccentricity of nearly 1 is a very elongated oval. An eccentricity equal to 1 is a parabola. Most of the planets have orbits that are not very eccentric, as shown in Appendix J and are thus close to being circles. The length of time it takes for a planet or other body to travel a complete elliptical orbit around the sun is called the orbital period. Kepler's second and third laws. In addition to discovering the true shapes of planetary orbits, Kepler found that an imaginary line between the sun and a planet sweeps out equal amounts of area in equal amounts of time. As illustrated in figures 29-4, this is known as Kepler's second law. Kepler also derived a mathematical relationship between the size of a planet's ellipse and its orbital period. He found that the square of the orbital period, p, equals the cube of the semi-major axis of the orbital ellipse. This relationship, called Kepler's third law, is p squared equals a cubed, where p is a unit of time measurement in Earth years and a is the unit of length measured in astronomical units. You will apply Kepler's third law to each planet in our solar system in the problem-solving lab later in this chapter. While Kepler was developing his idea, Italian scientist Galilei became the first person to use a telescope to observe the sky. Galileo made many important discoveries that supported Copernicus's idea that the planets, including Earth, orbit the sun. Most famous of Galileo's discoveries was the 4 moons orbit the planet Jupiter. This observation proved that not only does celestial bodies orbit Earth, and therefore Earth is not necessarily the center of the solar system. The underlying explanation for this heliocentric model still remained unknown. However, until 1684, when Spanish scientist Isaac Newton published a mathematical and physical explanation of the motions of celestial bodies, Newton's concepts included the law of universal gravitation, which provide an explanation of how the sun governs the motions of the planets, gravity, and orbits. Newton developed an understanding of gravity by observing the moon's motion, the orbits of the planets, and the acceleration of falling objects on Earth. He realized that any two bodies attract each other with a force that depends on their masses and the distance between the two bodies. This force grows stronger in proportion to the product of the two masses, but diminishes as the square of the distance between them. For example, if the distance between Earth and Moon were twice as great, the gravitational force between them would be only 1/4 as strong. At their normal distance apart, if the mass of the Moon were doubled and the mass of Earth were tripled, the force would be greater by a factor of 6. Gravity. Newton's statement of the relationship among the masses of two bodies and the force and distance between them is known as the law of universal gravitation. The law can be stated as follows. Every pair of bodies in the universe attract each other with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between them, or F is equal to G m over m sub 1 m sub 2 over r sub 2, or r squared. F is the force measured in newtons, and G is the universal gravitational constant, or 6.6726 times 10 to the negative 11th meters cubed per kilometer per second squared. M sub 1 and m sub 2 are the masses of the bodies measured in kilograms, and r is the distance between the two bodies measured in meters. Center of masses. Newton also determined that each planet orbits a point between it and the sun called the center of mass. The center of mass is the balance point between two orbiting bodies, similar to the pivot points on a seesaw. If one person on a seesaw is much heavier than the other, the balance point is closer to the heavier person, as shown in figure 29.5. In space, the same is true. If one of the two bodies orbiting each other is more massive than the other, the center of mass is closer to the more massive body. If the two bodies have similar masses, the center of mass is near the middle position between them. For any planet and the sun, the center of mass is just above the surface of the sun, or within the sun, because the sun is much more massive than any planet, as you will learn in the following sections.